Hi, this is Schwartz from MasterMathMentor.com. This is video AB17a, and the topic is straight line motion. It covers the AB manual pages 94 through 96. Now that we have covered related rates, we talk about a special related rates problem called straight line motion. Straight line motion is all around us, and we usually consider it in calculus in a horizontal direction or a vertical direction. Write down some real-life applications for straight line motion in the horizontal direction and in the vertical direction. When we talk about motion along a straight line, it could be a car, a bike, a person. We don't want to get into what is actually moving, so we use the generic term a particle that represents whatever is moving along a straight line. There are certain terms that we will be using in this section and variables to represent them. First, we start with time, which could be measured in seconds, minutes, hours, or whatever time unit you choose. The variable usually used is t. The position function represents where on a straight line you are as a function of t. If it is a generic straight line, we probably call it s of t. If a particle is moving along the x-axis, we will probably call its position x of t, and on the y-axis, y of t. Velocity. Velocity is always v of t. Speed, which is not the same thing as velocity, is the absolute value of v of t. Speed is always positive. Finally, acceleration we call a of t. Suppose a particle is moving along the x-axis, and its position is given by x of t is equal to t squared minus 2t minus 3. We look at a number line and we evaluate the expression x of t at values t equals 0, 1, 2, 3, 4, and 5. At t equals 0, our particle is at negative 3. At t is equal to 1, our particle is equal to negative 4, which means it is moved to the left. At t equals 2, our particle is back to negative 3, so it has moved to the right. At t equals 3, our particle is at the origin, which is 0. And at t is equal to 4, our particle has moved all the way out to 5. We show that on the number line. When an object moves, its position changes over time. We say that the velocity function v of t is the instantaneous change of the position function s of t over time. We know this to be a derivative, and we define v of t equal to s prime of t. Velocity is measured in linear units per unit time, for example, feet per second. We define the sign of velocity in the following way. If our object is moving along a horizontal line, v of t negative means that the object is moving left. V of t equal to 0 means that the object is stopped. V of t positive means that the object is moving right. If our object is moving along a vertical line, v of t negative means that the object is moving down. V of t equal to 0 again means that the object is stopped, and v of t positive means that the object is moving up. Speed is defined as the absolute value of v of t. Speed is not the same thing as velocity. Both give information as to how fast an object is moving, but velocity gives the direction while speed does not. So the speed of an object is always positive or zero. The definition of the acceleration function, a of t, is the instantaneous change of velocity over time. We know this to be a derivative, and thus can say that a of t is equal to v prime of t. But since v of t equals s prime of t, we can say that a of t is equal to s double prime of t. Acceleration is measured in linear units per unit time, or linear units per time squared. Since acceleration means change of velocity, usually there is some type of external force to provide acceleration or deceleration. In still air, wind can provide acceleration, and in water, current can do the same. In a car, we have two devices to change the velocity, the accelerator and the brake. So for convenience sake, we define the sign of a of t in the following way. Suppose we're traveling along a horizontal line. If the acceleration is less than zero, the object is accelerating to the left. If the acceleration is equal to zero, then the velocity is not changing. If the acceleration is greater than zero, then the object is accelerating to the right. If we're moving along a horizontal line, if the acceleration is less than zero, then the object is accelerating downwards. If the acceleration is equal to zero, then again, the velocity is not changing. And if the acceleration is greater than zero, then the object is accelerating up. Suppose we have a particle moving along the x-axis with position function s of t equals t squared minus 4t plus 2. We would like to determine what is happening during the first 5 seconds of movement of this particle. And then we would like to show where the particle is on the number line. We know that the velocity v of t is the derivative of the position function, so v of t equals 2t minus 4, and we also know that the acceleration, a of t, is the derivative of the velocity function, making it 2. On the table, there are values of t running from 0 to 5, and s of t, v of t, the absolute value of v of t, a of t. Stop the video and do the math and fill in the values for this table. We will then analyze it. At t equals 0, s of t equals 2. V of t is equal to negative 4, which means the particle is moving left. And a of t is equal to 2, which means that the particle is accelerating to the right. A particle does not have to have zero velocity at t is equal to 0. Think about taking a video of something that is moving. When you start the video, it very well may be that that particle is in motion. At t equals 1, s of t equals negative 1, v of t equals negative 2, and a of t is equal to 2. Which means that the particle is still moving left, but it is going slower. There is still an acceleration to the right. At t is equal to 2, s of t equals negative 2, v of t equals 0, and a of t is still 2. Since v of t equals 0, the particle is stopped, but there still is that acceleration to the right. Think of this as a particle being stopped, but being subjected to a wind that is blowing to the right. At t equals 3, s of t is equal to negative 1, v of t is 2, and a of t is still 2. So now the particle, because of that acceleration to the right, is now moving to the right and still accelerating to the right. At t equals 4, s of t equals 2, v of t equals 4, and a of t is still 2. So the particle is moving to the right, but faster, still accelerating to the right. At t equals 5, s of t equals 7, v of t equals 6, and a of t is still 2. So the particle is moving to the right faster yet, and still accelerating to the right. We now plot s of t, the position, based on the given values of t. When t is 0 and 4, the particle is at 2. When t is equal to 1 and 3, the particle is at -1. When t equals 2, the particle is at -2. And finally, when t is equal to 5, the particle is at 7. Remember that this motion is occurring along the x-axis. We show a slight curve to it so that we can see where the particle is moving left and then the particle is moving right. Students generally understand velocity, but get confused with acceleration. Let's take a look at two different situations. A equals 0 does not necessarily mean that v is equal to 0. Think about a car with cruise control. The car you see here has set cruise control to 70 miles an hour. That means it will always be traveling at 70 miles an hour, which means that there is no acceleration. So in this case, a is equal to 0, but v, for a period of time, will equal 70. And a greater than 0 does not necessarily mean that v is greater than 0. We see a biker who is biking to the left, so v is negative. He all of a sudden encounters a strong wind, making a to be positive. The biker will not start flying to the right. He will continue to go to the left, but at a slower rate. All of this can be summed up by the table. We show three possibilities for v. V being positive, v being 0, v being negative. We also show all possibilities for a being positive, a being 0, and a being negative. That sets up 9 different situations. Let's analyze each of them. Our first situation is v equals 0 and a is equal to 0. This is the easiest. We are stopped and there's no acceleration, which means that we're not going anywhere. Next, v equals 0 and a is greater than 0. V equals 0 means we're stopped, but we are accelerating to the right, which means that within a second or two, we expect to be moving to the right. If v equals 0 and a is less than 0, it means we're stopped, but accelerating to the left. So within a second or two, we expect to be moving to the left. If v is positive and a is positive, that means we are moving to the right and accelerating to the right, which means that we are speeding up. If v is positive but a is 0, that means we are at a constant velocity moving to the right. That is cruise control. If v is positive and a is negative, that means we are moving to the right but accelerating to the left. That means we're slowing down. Think of this as biking into a wind or swimming against a current. If v is negative and a is positive, that means we are moving to the left, but accelerating to the right. That means we are slowing down. If v is negative and a is 0, that means we are moving at a constant velocity to the left. Think of this as cruise control moving to the left. If v is negative and a is negative, that means we are moving to the left, but also accelerating to the left. That means we are speeding up. Think of this as biking with a tailwind or swimming with the current. Rather than memorize this chart, a good way of remembering it is to look at the signs of both V and A. If they are the same, whether they're both positive or both negative, that means that the particle is speeding up. If they have different signs, that means that the particle is slowing down. Doing the type of analysis we just did for a particle in motion at every second is very time-consuming. It can be simplified. We are concerned with three things: the direction of the particle, when it is stopped, and intervals when it is speeding up and slowing down. In order to do this, we will develop sign charts for velocity, acceleration, and a third chart for motion, which will be the product of velocity and acceleration. We will develop this procedure for a particle moving along the x-axis with position function s of t equal to t squared minus 6t minus 2. We start by taking the velocity and setting it equal to 0. 2t minus 6 equals 0 and t equals 3. That represents the time that the particle is stopped. So we now make a sign chart starting with t equals 0 and t equals 3. And we find that the velocity is negative in the interval 0 to 3, 0 at t equals 3, and positive to the right of t is equal to 3. This tells us that the particle is moving left, stopping, then moving right. We next find the acceleration, which is equal to 2. That's always a positive number, so the sign chart for acceleration is always positive. Next, we then multiply the signs of velocity and acceleration. In the interval 0 to 3, we get negative, and from 3 to infinity, we get positive. This is interpreted as the particle is slowing down from t equals 0 to t equals 3, and then speeding up from t equals 3 on to infinity. Finally, we would like to make a position graph to see how the particle moves along the x-axis. We take our velocity, set it equal to 0, and get t equals 3. This is a critical time. Something happens at t equals 3, the particle is stopped. T equals 0 is always considered to be a critical time. So we need to figure out where the particle is at t equals 0 and t equals 3. So plugging 0 into the S formula, we get negative 2, and plugging 3 into the S formula, we get a negative 11. So we know that at t equals 0, our particle is at negative 2. At t equals 3, our particle is at negative 11. And from our sign chart for velocity, we know that our particle is moving left, stopping, and then moving right. So we see that in the graph, as the particle moves left to t equals 3, and then moves right forever. Again, we put a curve on it so that we can show the motion along the straight line. In 3b, our particle is moving along the x-axis with position function s of t equal t cubed minus 3t squared. I generally like to take the velocity and acceleration, set them equal to 0 immediately. So v of t equals 3t squared minus 6t equals 0, t equals 0, and t equals 2. A of t equals 6t minus 6, set equal to 0, t is equal to 1. We make our sign chart for velocity and find that between t equals 0 and t equals 2, the velocity is negative, meaning that the particle is moving to the left. To the right of t equals 2, the particle is moving to the right. We then look at a of t. Between 0 and 1, the acceleration is negative, and after 1, the acceleration is positive. Note that acceleration by itself tells you nothing. You must multiply the signs. So in the interval 0 to 1, the velocity times the acceleration is positive, meaning that the particle is speeding up. Between 1 and 2, velocity is negative, acceleration is positive, so when we multiply the signs, we get a negative, and that means the particle is slowing down. And finally, to the right of t is equal to 2, velocity is positive, acceleration positive, and that means when we multiply the signs, we get a positive, and that means that the particle is speeding up. So the particle speeds up, then slows down, then speeds up. In order to analyze the position of the particle, we again set v of t equal to 0 and get 3t squared minus 6t equals 0, or 3t, t minus 2 equals 0, and t equals 0, and t is equal to 2. These are the critical times. T equals 1 for acceleration is not a critical time because the particle does not turn at t is equal to 1. So s of 0 is equal to 0, and s of 2 is equal to negative 4. We show this on our number line. At t equals 0, the particle is at the origin, and at t equals 2, the particle is at negative 4. And looking at our velocity chart, our particle moves left for the first 2 seconds and then moves to the right forever. Number 4 is a typical problem from the AP exam on straight line motion. For the particle moving along the x-axis with position s of t equals t cubed minus 9t squared plus 24t plus 4, determine intervals when the particle is moving left, right, speeding up, and slowing down. Justify your answer. Draw a graph showing its position at critical times. We start our procedure by finding v of t, which is 3t squared minus 18t plus 24, and set it equal to 0. That gives v of t equals 3, quantity t squared minus 6t plus 8 equals 0. Factor it into 3, t minus 2, t minus 4 equals 0. So our critical times are t equals 2, t equals 4, and of course t equals 0. We will also find a of t, which is 6t minus 18, set equal to 0, and t is equal to 3. Sign charts. We make a sign chart for v of t with the critical times of 0, 2, and 4, and find that v of t is first positive, stopping at t equals 2, then negative, stopping at t equals 4, and then positive. We make a second sign chart for a of t and find that a of t is negative in the interval from 0 to 3 and then positive. So multiplying the signs, we get from 0 to 2, positive times negative, which is negative. From 2 to 3, we get negative times negative, which is positive. From 3 to 4, we get negative times positive, which is negative. And from 4 onward, we get positive times positive, which is positive, meaning that our particle is slowing down, then speeding up, then slowing down, then speeding up. In the AP exam, you must clearly state your answers. The readers do not want to have to search your work trying to find it. Also, you must justify your answers. Sign charts are never justifications. They may help you to determine the answers, but you have to give an answer that reflects your knowledge of calculus. This is how to properly answer the questions. The particle is moving right on the interval 0 to 2 and 4 to infinity because v of t is positive in those intervals. It is moving left on the interval 2 to 4 because v of t is negative in that interval. The particle is speeding up on the interval 2 to 3 and 4 to infinity because v of t and a of t have the same signs in those intervals. It slows down on the intervals 0 to 2 and 3 to 4 because v of t and a of t have opposite signs. Finally, the position graph. We know that the particle at t equals 0 is 4, at t equals 2 it's 24, and t equals 4 it is 20. We know also that the particle is moving right from 0 to 2 seconds, moving left from 2 to 4, and then moving right from 4 to infinity. The graph shows all of that information.